Hi everybody. Today is the Monday 18th of March, and what I'm going to do today is I'm going to talk about the lab of sophomore. That's the what I did. I typed it in the EL228. It's about AC simulation of electrical circuits, which is going to show you in two parts. The first one, I'm going to use the PSPICE to draw the circuit and show you the output plot, and also I'm going to use the LTSPICE IV also to show you the plot. Well, let's get started. What are we going to do today is in general, this is the circuit that we will do the simulation. Actually, it's the simple RLC circuit in our series, and that's we call we're going to see the frequency response of RLC circuits, RLC series resonance circuit. Okay, let's get back to the basic understanding first. As we know that there are only three components that we're going to use, for the circuit, which has the R, C or capacitor, and also our inductor or L. And our student also know that for the impedance or resistance R, the resistance doesn't change with the frequency, but for C, the impedance is going to change with frequencies as well as the inductor. And you know that impedance of our capacitor is the 1 over j omega c, and that's your omega is the 2 pi f. And if you noticed, when the frequency increasing, this means that your impedance of your capacitor is going to decreasing. Is the inverse proportional, to the frequency. I mean, in the term of impedance. And for inductor, this is direct proportional to the frequency. I mean the impedance, which is equal to j omega L or j 2 pi f L. So they work out, in opposite way. I mean, talking about capacitor and inductor. And for the RLC circuit, we also know that I'm not going to look back at how to calculate for resonance frequency, or F0 equal to 1 over 2 pi square root of LC. And that means at this frequency you're going to have the maximum current flow in the circuit. So what I have in front of the monitor is just I'm going to put R equal to 50 ohms, and inductor is the inductance is the 6.8 microhenry, and for capacitance going to be 220 picofarad, and also have input voltage. Okay, let's take a look quick. Okay, let's finish this one first. This is just for simple calculation. Let's apply your KCL from the circuit. If you're looking for like V out, you can calculate simply use the Ohm's law. Alright, this is your V out. So basically your V out is going to be the current flowing through capacitor C1, and then multiplied by the impedance of C1, which is J 1 over j omega c. So what you can do is that you can start do calculation. So your V out is going to be let me get this one. V out equal to our IC multiplied by XC, which is the impedance of a capacitor, and your V in, since it is the series circuit, so our I equal to V in divided by total impedance. So that means equal to R plus XL plus XC, and then you multiply by XC, right? That's the impedance of our capacitor. And then you can plug it in, XC equal to 1 over J omega C. R is still the same. XL is equal to J omega L, and then XC equal to 1 over J omega C. And you rearrange the term, and then what you can do is the simple math. This one I divided by J omega C, so you multiply by J omega C to R, and then J omega C multiplied by J omega L. You got the negative omega L square LC, and then J omega C divided by J omega C. Let's give you 1. So put the real term together, so you have like 1 minus omega square LC, right? And this is the imaginary part, so this become J omega RC. And then you also rearrange the term again, so you multiply this one, just simply change this to be the opposite sign. So I have 1 minus omega square LC minus J omega RC, right? And this is the same thing. So you have 1 minus omega square LC minus J omega RC divided by this term square plus this term square. Okay, that's simple math. And you can rearrange the term. You have the real part and imaginary part for V out. So this is the real part, and this is your imaginary part. Okay, let's get to the circuit. Let's start with the PSPICE first. Okay, just remind you about how to work on that one. Okay, you open the new schematic and then Control G. You want to get the V sign, alright, as the input source or input voltage. And then you look for R. Okay, and then Control G, look for L, and then you also Control G, get new part, and then you look for C. So you type C, and then you simply rotate Control R. Right. Let's see, I don't need this one. And what happened to this? Alright. Okay. And then you also need ground, A, G, and T. Okay, and then you make a connection wire, Control W. Oops, sorry. Alright, start over again, Control W. And then the next step is you need to change the value of your C, your L, and your R. Alright, so what you can do, you double click this one. I'm looking for somehow it doesn't respond. Alright, I'll go to edit and go to attribute. I need this one to be 50 ohms for R, and then you go to L. I need this one to be what, 6.8 microfarad. I'm sorry, Henry, microhenry. And for C, I'm going to use 220 picofarad. So I put 220 P, that's picofarad. Alright, so the next thing what we're going to do I'm going to set up the attribute of the AC. Let's put as the 1 peak to peak V offset, DC offset. I don't need it, so put as 0. And then amplitude still have to put 1. And then frequency I'm going to put like 100 Hertz. You can make up any number you want. Alright, so we're ready to do simulation, but before that we need to go to analysis, and need to go to setup, and then you're looking for AC sweep, because we're looking for the frequency response. And since it's going to start from 10 Hertz or whatever, like 100 Hertz, that's fine. And I'm gonna put N at the 10 megahertz, so that's MEG. Click OK. So you're ready to do the simulation. And then I also, as the reference, let's put this one as the V out. I have problem with this one. Edit. Let's see, attribute. Somehow my mouse doesn't look very good. Alright, sorry. See, working to label. Alright, okay. Just V out. Here we go. Alright, let's do analysis. You go to F11, or you do simulation. Ask you to save, first. Do whatever, just put whatever the name is. Now is that's going to show you the plot. I go to this one, the address icon, and I'm going to plot that dB, right, decibel, and then you put V out, and that's the gain is mean the V out divided by V in, and my V in is what is the V1, right? So I go to V1 plus divided, so it's become the gain in the unit of dB. So this is my plot. As you can see that this is actually is the bandpass filter. I'm gonna blow this up a little bit, and if you put the cursor, this is become your F0, right? The centering frequency, and your bandwidth. Actually, you can find it from you go to the top, right? And then you use the left click of your mouse. You go down here, just about 3 dB, and that's going to give you the cut low and cut high. High is on the right, low cut is on the left, and the frequency of high cut and low cut. The difference is going to be the bandwidth, and your F0 or the centering frequency is actually become the bandwidth divided by 2, as I wrote in I type it in Microsoft Word here, and as I show you this is become the bandpass frequency response, bandpass filter, sorry. And this is your high cut is become F0 centering frequency plus the bandwidth divided by 2, and also for the cut low frequency cutoff FCL actually become a centering frequency minus the bandwidth divided by 2. And you also know the bandwidth have the relation with the Q factor, be bandwidth equal to F0 divided by Q. Q is the quality factor, or we call our inner band pass filter. It can be characterized by the Q factor. What does it mean, Q factor? Q factor is the reciprocal or inverse proportional to the fractional bandwidth. If you have a high Q filter, that means you have the narrow bandwidth or pass band, But for the low Q, it shows that you're going to have the wide pass band, right? So according to this equation, BW or bandwidth equal to F0 divided by Q. Okay, that's pretty much about our PSPICE simulation. As you can see, this is the bandwidth, and this is the the frequency response. So it's very simple. And now let's move to LTSPICE IV. Okay, that's the objective, or the lab is going to use the LTSPICE IV. So let's start with the new schematic. Okay, we're going to start drawing the circuit. So you need ground, right? And then you need R. Let's rotate this one for R. Left click of the mouse to place, right click to stop, and then you need C capacitor, right click to stop, and you also need inductor, and we need to rotate because this is going to be series RLC circuit. Okay, and I also need the source voltage, so click this one icon component and look for the voltage. It's very simple. Left click to place and right click to stop, and then you go or make connections. So you go to wire, then you start making a connection. Oops, sorry. Let's cut this one. Sorry. Alright. Redo again. C1, and going to make connection to ground. So you move ground, you go to move F7, you left click, and you can move your ground. Alright, go wire again. So alright, and let's finish this up. Okay, next step is you need to change the value of your resistor. This one I'll put as the 50, right, ohms. And for inductance, right click and you change the value to be 6.8 microhenry. Click OK. And also C1, I need like 220 picofarad, so you put 220p. And now for the input voltage, make right click, you go to advanced. We're going to use the small signal AC analysis. So AC amplitude, I'm going to put 1 volt peak to peak, so it's become 1 VPP. Okay. P. And for AC phase, the phase difference, I'm going to put to be a 0. And then you click OK. And now you're ready for the simulation, but you need to go to setup first. You go to edit, the main menu, edit and PSpice analysis. So you go to AC analysis because you want to see your frequency response. The type sweep have to be octave. Number of point per decade, let's say 100, doesn't matter. Start frequency, I'm gonna put like 10 hertz, and you end up with 10 meg. Okay, MEG. And that's become AC analysis, or type of sweep to be octave, and start number of points per octave is 100, and then start frequency is 10, and then stop frequency is 10 megahertz. You click OK, and you place the details right down here. Okay, now what else you need to do? We're ready to do our simulation, right? So let's try go to the main menu, or you go to run. Oops, sorry. Actually, I should put this one as the reference to be V out. I forget. Alright, whatever, doesn't matter. But actually, you're going to put this one as the label as V out, mark reference. Okay, and then let's see, label net. I'm not sure to do this one, but let's try it. V out. Oops. Okay. And then let run again. So you're going to see your plot window pop up. Okay. So this is the detail and of whatever from our simulation. So let's get to the plot. You go to plot setting, you go to address, and then you're looking for, sometimes it's like it doesn't show V out, but if you take a look at this one, you're not sure which one is your V out. You have like N001, N002, N003. Okay, what you can do is cancel this one out. You go to your circuit, and then minimize the window, and you go to where's my circuit? Oops. It's supposed to be some. Oh, sorry. You go to this is minimize. This is your circuit, right? You maximize. Alright, you wanted to see the detail since I already put V out as reference, but somehow it doesn't show up. You go to I think it's become net list. It's somewhere around here. Not analysis. Okay, cancel. Sorry, this will take a moment. File. Viewer. Yeah, it's going to be this one. Piece by net list. Okay, as you can see, you can use this one as the reference as well. So your R1 is make connection between N002 and N001, and you know that this has become the node of N001, and then to the node N002, and the value is 50 ohms, right? And for C1, this is right here, so it's connected to from the node N003 to 0. That's mean ground, and the value is 220 picofarad. So this one is become the node N003, and for L1 you can see that it's connected between the node N002 and N003. So this one is N002 and this is N003. So I use this one as the reference to plot your output. Okay, so let's get back to your plot, just right here. And then you go to plot setting, you go to address, and then this is your V in V out. So you click OK. As you can see, this is your the frequency response is become a bandpass filter, and the unit of the gain is become decibel. Obviously, it shows here on the scale, and you also can change the scale or on the y-axis. Simply right click and you go to left click. You see the ruler here, you make a left click and you can see representation. This is body plot, and I put the unit of the gain in decibel. You can put also in linear, okay, just like this one. So the unit it simply is the V out divided by V in, but for decibel you have like 20 log of or V out over V in. Okay. Oops. What did it do? Let's try. Oops. Let's put left. This is decibel. Cancel. And then I'll zoom back. No. Let's start over again. I don't want to waste my time on this one. So okay. Go to the circuit. Go to run. And later on I will explain to you where is the F0 centering frequency and the cut high and cut low frequency. Okay, let's get to the plot, you go address here, and this is your V out, the gain V out divided by V in. Okay, now you want to see the cursor, right? This has become your, let me get this one, cannot. This has become your centering frequency. Go to my group. Okay, yeah, this is your centering frequency. And you know that for cut low and cut high, what you can do is that this is the peak of your frequency response, and you go down to what, 3 dB, right? That's going to give you on the left, it's going to give you cut low frequency, and on the right you drop down to 3 dB. That's going to give you what, cut high, right? And the difference between the cut high frequency and the cut low frequency is the bandwidth. Okay, so what you can do, you can get your cursor. Actually, what you can do is to get the cursor. If I still remember, I did that before. I already have the grid. Oops. Let's put the grid back. Plus setting grid, and then go to the output. I kind of forget. Actually, it's on the left. Body plot. Okay, let's continue. Alright, to get the cursor, you simply, put the mouse on the V in 003 or left click. Okay, and this is going to give you a cursor. So you can move around, use the right arrow key. You put this one on your, see that, on the plot, and you start moving, to the right, and you can look for the cut low frequency and cut high frequency, and also centering frequency. Okay, let's take a look at the centering frequency, or F0. Okay, I'll put this one on the peak. So you notice this is the frequency at what become 4.0 megahertz. Alright, that's the F0. And if you want to see your cut low frequency, you simply go to this is the magnitude, is the 10.99 or just about 11 dB, right? That's your gain. And if you're looking for the cut low frequency, it means you have to drop this down to 3 dB. So from 11 drop by 3, so that's you're going to have what, 8, right? So you move cursor, left cursor to the left, and then you're looking for 8 decibel. So this is about 7.99, so let's make it as close to what, 8. Okay, from 11 to 8, so you drop 3 dB, and thus the cut low frequency going to be 3.387 megahertz. Okay, also for cut high frequency, you go to the right of F0, and then you can look for drop down to about 8, 0.0. So you can estimate your cut high frequency. So that's close to 4.5 megahertz. And the difference between the cut high frequency and the cut low frequency does give you what, the bandwidth, just like this one, cut low and cut high. and you can also look for Q that's equal to F0 divided by bandwidth, right? That you can get information or get the number from the plot. Okay, so that's pretty much for about the lab LTSPICE IV, for to do AC simulation of electric circuit analysis, or the series resonance RLC circuit. And I will continue with part 2 of the lab, and that's we're going to meet on what, 29th of March. That's Friday, so it's coming soon, the next week, not this Friday. That's going to be about talk about the common collector circuit, and we're going to see the frequency response. Alright, I'll see you later. Thank you. Bye.